Bridge. Counting compute without getting lost. Training large language models requires enormous computational resources. You may have heard statements like, GPT-3 used 3.14 times 10 to the 23rd floating point operations, or this model was trained on 500 GPUs for 2 weeks. These numbers sound impressive, but what do they actually mean? And why should we care about counting operations so precisely? We'll explain why measurement matters and how to think about computational cost. When we say training a model requires a certain number of operations, we're quantifying the total amount of arithmetic the computer must perform. The standard unit is the flop, which stands for floating point operation. A floating point operation is a single arithmetic step performed on numbers with decimal points, an addition, multiplication, subtraction, or division. Modern processors perform billions or trillions of flops per second, so we use abbreviations. Gigaflops is billions per second, teraflops is trillions per second, and petaflops is quadrillions per second. Why count flops at all? Because computational cost is the limiting factor in language model development. Training a state-of-the-art model can cost millions of dollars in hardware time. If we want to predict how long training will take, or compare the efficiency of different model architectures, or decide whether a research idea is feasible, we need a way to estimate compute. Flops provide that currency. They let us say, this operation costs this much, this architecture costs that much, and therefore we can or cannot afford to try it. But counting flops is not as simple as adding up every operation. The key insight is that most of the computation in neural networks happens in matrix multiplication. A matrix multiplication takes 2 rectangular arrays of numbers and produces a third array by systematically multiplying and summing elements. If you multiply a matrix of size m by k with a matrix of size k by n, the result has size m by n, and computing it requires m times k times n multiplications, plus nearly that many additions. For large matrices, this quickly becomes billions of operations.
In a transformer language model, nearly all computation is matrix multiplication. When tokens are projected into hidden states, that's matrix multiplication. When attention scores are computed, that's matrix multiplication. When feed-forward layers transform representations, that's matrix multiplication. Because matrix multiplication dominates, we can estimate total compute by counting the shapes of these matrix operations.
M by n matrix C. Each element of C is the dot product of a row from A and a column from B. Computing all m times n elements requires m times n times k multiply add operations. If m, k, and n are all 1,000, that's 1 billion operations. If they're all 10,000, it's 1 trillion operations. The cost scales as the product of 3 dimensions, which grows rapidly as models get larger. Modern hardware is designed to make matrix multiplication fast. GPUs and TPUs have specialized circuits called tensor cores or matrix engines that can perform large matrix multiplications in parallel. These circuits achieve much higher throughput.
If we know the model has 12 billion parameters, the batch size is 100, and the sequence length is 2,000 tokens, we can calculate roughly how many flops a single training step requires. The standard formula for training compute is approximately 6 times the number of parameters times the number of tokens processed. Where does the factor of 6 come from? It arises from the forward and backward passes. During the forward pass, the model processes input tokens through all its layers, performing matrix multiplications at each step. The total cost is roughly 2 flops per parameter per token, 1 for the multiplication and 1 for the addition in the multiply-accumulate operation. During the backward pass, we compute gradients, which involves 2 more matrix multiplications per layer, 1 to compute gradients flowing backward through activations, and 1 to compute gradients with respect to weights. This doubles the forward pass cost, giving us 4 flops per parameter per token. Add the forward pass again, and you get 6. This 6ND formula is a remarkably good approximation for transformer models, where n is the number of parameters and d is the number of tokens. But why do we care about such precise accounting? Because when you're training a model for days or weeks on hundreds of GPUs, even small inefficiencies compound into wasted resources. If you miscalculate the batch size and run out of memory, the training crashes. If you misjudge the compute requirements and under-provision hardware, training drags on far longer than planned. Conversely, if you optimize operations to reduce unnecessary flops, you can train faster or fit larger models within the same budget. Precision in accounting enables precision in planning.
Another reason to count compute is to understand algorithmic improvements. Suppose someone proposes a new attention mechanism that reduces the cost of self-attention from quadratic to linear in sequence length. How much does that save? It depends on the sequence length and the relative cost of attention versus other operations. By counting flops, we can quantify the benefit. If attention currently consumes 30% of total compute, and the new mechanism cuts that in half, we save 15% overall. That might be worth the implementation complexity, or it might not. Without counting, we're guessing. Matrix multiplication is so central that it's worth understanding its structure. Consider multiplying an M by K matrix A with a K by N matrix B to get an output than general purpose cores. However, they require data to be arranged in specific formats and depend on fast memory bandwidth. This is where the distinction between compute-bound and memory-bound operations becomes important. An operation is compute-bound if the bottleneck is the speed of arithmetic circuits. Matrix multiplication on large matrices is typically compute-bound. The hardware can keep performing multiplications as fast as data arrives. An operation is memory-bound if the bottleneck is the speed of moving data between memory and processors. Small matrix multiplications, or operations like element-wise addition, are often memory-bound. The hardware sits idle waiting for data.
Understanding whether an operation is compute-bound or memory-bound tells you where to optimize. The paired lecture will show you how to implement BPE tokenization and how to count the flops in matrix operations precisely. You'll see derivations of the 6ND formula and learn how to account for additional operations like attention and layer normalization. To follow that lecture effectively, keep these mental models in mind. Flops are the currency of computation. Matrix multiplication is where most flops are spent. The 6ND formula captures the dominant cost of training, and understanding compute cost enables planning and optimization. Why does this matter beyond the mechanics? Because computational cost determines what's possible. 10 years ago, models with 100 million parameters were large. Today, models with 100 billion parameters are common. This 1,000-fold increase is possible partly because hardware improved, but also because researchers learned to use compute more efficiently. Every percentage point of efficiency gained means bigger models, faster experiments, or lower costs. For researchers, this translates to more ideas tested. For companies, it translates to lower bills. For the field, it translates to faster progress. Resource accounting also forces honesty. When someone claims a new model is efficient, we can check. Did they count total flops or just inference cost? Did they compare models of the same size or different sizes? Are they accounting for memory or only compute? Precise accounting cuts through hype and lets us evaluate claims rigorously. This is especially important as models grow larger and more expensive, and as claims about efficiency multiply.
Another dimension is the relationship between flops and parameters. More parameters generally mean more flops per token, but also potentially better performance. The question is, what's the right trade-off? Should we train a small model on lots of data, or a large model on less data? This question can only be answered by comparing flop budgets. If you have a fixed compute budget, you can train a billion parameter model on 1 trillion tokens, or a 10 billion parameter model on 100 billion tokens. Which is better depends on scaling laws, which we'll encounter in later lectures, but the analysis starts with counting flops. One subtlety is that not all flops are equal. A flop performed on a GPU tensor core is much faster than a flop performed on a CPU. A flop in a large matrix multiplication is faster than a flop in a small one, because hardware can amortize memory overhead. This means wall clock time doesn't always correlate perfectly with flop count. Two models with the same flop count might take different amounts of time to train if their operations have different hardware characteristics. This is why benchmarking on real hardware is important, even when theoretical flop counts are available. The paired lecture will also discuss implementation details like half-precision arithmetic and mixed-precision training. These techniques reduce memory and increase speed by using 16-bit floats instead of 32-bit floats for some operations. How does this affect flop counts? Technically, a half-precision flop is still a flop, but hardware can perform twice as many per second, so the effective throughput doubles. This is another reason why raw flop counts must be interpreted carefully in the context of hardware capabilities and data formats.
As you listen to the paired lecture, notice how each technical detail connects to resource management. When BPE's implementation is described, think about how tokenization cost scales with text length and vocabulary size. When matrix multiplication is analyzed, think about how the dimensions of weight matrices were chosen and what constraints limited those choices. When the 6ND formula is derived, think about what it implies for training different model sizes and how it guides decisions about compute allocation. Counting compute might seem like an accounting exercise, but it is fundamental to the engineering discipline of machine learning. Without careful measurement, we cannot plan experiments, optimize systems, or evaluate progress. The paired lecture will give you the tools to perform this measurement rigorously. Your task is not just to follow the derivations, but to internalize the intuition. Where does compute go? Why does it matter? And how can we use it wisely? In summary, we've established why flops matter, how matrix multiplication dominates cost, what the 6ND formula represents, and why precise measurement enables better engineering. The next lecture will give you the mathematical details and implementation techniques to count compute accurately. Listen for the connections between abstract costs and concrete constraints, and you'll come away not just with formulas, but with a sense of how computational budgets shape the entire field of language modeling.